Hello and a huge welcome from Metricom. I'm so glad you could join us for this explainer. Today, we're diving into one of the trickiest environmental puzzles of our time, focusing on methods for the remediation of contaminated sites. Specifically, we're looking at the absolute beast of a task, cleaning up PFAS. You probably know them better by their more ominous nickname, forever chemicals. These incredibly stubborn, synthetic substances have made their way into our soil, our water, literally everywhere. But how do you actually clean up something that was engineered to last forever? Well, that's exactly what we're breaking down today, using insights straight from the Swedish Environmental Protection Agency's guidance on risk assessment and remediation.
Okay, let's dive into this. Here is the roadmap for our explainer today. We're going to start with the PFAS cleanup challenge, then look at remediating and containing soil pollution and treating contaminated water. Finally, we'll wrap up with some real-world cleanup experiences and what the future of remediation looks like.
All right, kicking things off with Section 1, the PFAS Cleanup Challenge, Battling the Indestructible.
So, this whole challenge is a classic case of unintended consequences. The very properties that made PFAS a commercial superstar back in the 1950s, repelling water and resisting heat, are what make them an absolute environmental nightmare today. They were perfect for frying pans, firefighting foams, and rain jackets, but they are terrible for our ecosystems. And the root of the problem? The carbon-fluorine, or CF bond. This is essentially the chemical superpower of PFAS. In organic chemistry, the bond between carbon and fluorine is ridiculously strong. It acts like an unbreakable chemical armor. Because of this bond, these substances just don't degrade naturally in the environment. While microbes can easily munch away at other organic contaminants, they literally bounce right off this CF bond. Which brings us to a massive, mind-bending dilemma. How exactly do we clean up the indestructible? When nature's usual recycling processes are totally powerless, human engineering has to step up, and scientists are actually developing some really ingenious counterattacks to break through that chemical armor.
That takes us right into Section 2, Remediating Contaminated Soil, the active defense.
When scientists go on the offensive to actively remove or destroy these chemicals from the ground beneath our feet, they rely on three main methods. First up is excavation. Now, you might be thinking, just dig it up, right? Well, PFAS molecules are surprisingly water-soluble and highly mobile. They don't just hang out on the surface, they penetrate really deep into the ground. That makes simple excavation surprisingly tough and very expensive. Next is soil washing. This involves basically transferring the contaminants from the dug-up soil into a washing liquid. It actually works pretty well for sandy soils, but here's the catch. You're left with highly contaminated water that then needs its own intensive treatment. Finally, there's high-temperature incineration, which is currently one of the only guaranteed ways to destroy the substance completely.
And that brings us to a really crucial number, 1100. We're talking 1100 degrees Celsius for at least 2 full seconds. That is the intense volcanic-level heat required to completely shatter that CF bond and destroy the chemical armor of PFAS, turning it into carbon dioxide and hydrogen fluoride. As you can probably guess, heating massive mountains of soil or waste to 1100 degrees requires an insane amount of energy, making it incredibly expensive.
Moving on to Section 3, Containing Soil Pollution, Trapping the Threat.
Because active destruction is so tough and so pricey, we often have to look at Plan B. On one side of environmental engineering, we have active remediation, removing or destroying the threat, like we just saw with incineration. But on the other side, we have containment. Containment doesn't kill the PFAS, it traps it right where it is. Engineers will install vertical barriers, like deep sheet piling, to literally divert clean groundwater away from the contaminated dirt. Or they use horizontal barriers, essentially capping the soil so rain can't soak through. There's also this fascinating method called chemical stabilization. They add specific substances to the soil that react with the PFAS, locking it in place and heavily reducing its ability to leach into the surrounding environment. The ultimate goal here? Protecting our vital groundwater.
Which leads perfectly into Section 4, Treating Contaminated Water, the Filtration Battle.
Water is honestly the most critical battlefield here since PFAS spreads so easily into drinking sources and private wells. When we look at the current arsenal for treating water, you're going to notice a frustrating pattern. Every single one of these technologies works brilliantly when it comes to efficiency, but they all come with major, costly drawbacks. Activated carbon is a workhorse, achieving over 99% efficiency, but it grabs all organic material, not just PFAS, so those filters saturate super fast. Ion exchange gives you great efficiency too, but it's really sensitive to any changes in the incoming water's natural chemistry. And then you've got membrane technologies like reverse osmosis and nanofiltration. They are incredibly effective, sure, but they leave behind a highly concentrated toxic sludge that you still have to figure out what to do with.
To really understand the difficulty here, just think about the sheer physical force required by reverse osmosis. We are talking about needing more than 100 bar of pressure. To put that into perspective, that is roughly the same crushing pressure you would feel 1,000 meters underwater. Forcing water through a tiny, semi-permeable membrane to leave the PFAS behind at that pressure is an absolute energy drain. It really drives home the point that there is absolutely no easy, cheap silver bullet for water treatment.
Let's head into Section 5, Real-World Cleanup Experience, looking at some Swedish case studies.
It's time to take these concepts out of the lab and see how they're being applied out in the real world. And it's actually really encouraging to see progress happening, especially at places like old fire training grounds where these foams were heavily used. Over at Kalmar County Hospital, a soil washing project managed a seriously impressive 96% removal rate for PFAS. Meanwhile, at major transit hubs like Arlanda and Landvetter airports, they're tackling highly contaminated stormwater. They found that natural stuff in the water like humus and iron were clogging up their activated carbon filters. So they innovated. They added extensive sand and bag pre-filtration stages to keep the system running smoothly. And we can't forget the former Tullinge F-18 air wing, which now runs a massive water treatment facility to handle contamination from an old rock hangar system.
There's one specific number that really stands out here, 99.98. That is the percentage of PFOS treatment efficiency achieved at that Tullinge air wing facility. Since 2012, they have processed an absolutely mind-boggling 80 million liters of water to hit that mark. It is a monumental logistical and engineering achievement, for sure.
But as always with forever chemicals, there is a catch, and we really need to understand this part of the challenge. Filtration, no matter how incredible that efficiency percentage is, doesn't actually destroy the PFAS, it merely captures it. Whether you're using activated carbon at an airport or reverse osmosis in a high-tech lab, you are literally just moving the forever chemical from the water into a filter. And what happens to those spent filters? Yep, they have to be packed up, transported, and incinerated at that volcanic 1100-degree temperature we talked about earlier. It's a continuous, relentless cycle of financial and energetic costs.
Finally, we arrive at Section 6, the future of remediation, looking ahead.
So what's next? What does all this ongoing research mean for our cleanup efforts? Well, tracking the timeline of our remediation journey really puts things into perspective. The very first PFAS were manufactured way back in the 1920s. For nearly a century, humanity pumped these chemicals into the world without fully grasping the fallout. It actually wasn't until 2008 that PFAS was officially banned in firefighting foam in the EU. And even as recently as 2019, when this guidance was published, a lot of remediation technologies were still firmly in the experimental stage. We basically gave the pollution a massive head start, and our technological response is still in its infancy, though it is evolving incredibly fast.
The Swedish EPA offers a very necessary, somewhat cautious reality check here. They make it clear that most of the remediation methods described are still at a relatively early stage of development, and full-scale field trials just haven't been performed yet. So we're definitely still far from a perfect one-size-fits-all solution. But there is absolutely hope on the horizon. Major research initiatives, like the Vinnova-funded projects over in Sweden, are actively grinding away right now to deliver the next generation of treatment breakthroughs for both soil and groundwater. I want to leave you with a final, slightly provocative thought to chew on. When we look at the immense energy required, the 1100-degree incinerators, the massive carbon filtration plants, and the billions of liters of water that demand treatment, we really have to ask ourselves, was the short-term convenience of water-repellent jackets and non-stick pans truly worth the centuries-long legacy of environmental cleanup we've left behind? It's a question that goes way beyond chemistry and engineering. It is fundamentally about the true cost of our modern advancements. Thank you so much for joining me for this explainer. Keep asking questions, keep learning, and we'll catch you next time.